Welcome to lesson 1, video 6, which is all about the functions in Leap. This is going to be a bit longer video because there's quite a lot to cover in these functions. In this video, we're going to talk about the functions in Leap, which is the main input method. There are other methods to inputting data into Leap, like importing from Excel, for instance. But the main method that we use is inputting data directly into Leap, which is done through the functions. We're going to have an introduction to the most important functions, which are the Interp, smooth, step, growth, growth as, and remainder functions. I will go through them individually and explain what they do, but these are the functions we're going to use 98% of the time. We will have an intro to the functions and branches windows. Those are for using functions that you don't normally use, so you can find them. It's kind of a small database for that. We will have an example on the function stacking, combining different functions, and we will also have a look into how to control your functions, help you identify what is in your functions, how they work by using the Builder tab and the Elaborate tab. So, a few words on functions. So the functions, as I said before, is the main input method for data into Leap. They remind you quite a lot of Excel formulas. It's the same principles. You put in some data in some way, and then you can plus, minus, do math between them. They can do quite a lot, but they're in form and function, they're quite the same as Excel functions. There is quite a large number of functions that could do a lot of different things, but the ones we're going to go through in this video are the ones that are by far the most often used, and also some of the simpler ones. We haven't talked about inherited scenarios yet. We will in one of the next videos, but functions are normally inherited through scenarios. That also means that links are inherited through scenarios, and then can differ in between those scenarios. That will make more sense when we go through the scenarios. But it's important to remember that generally speaking, unless otherwise specified, a function comes from its parent scenario. Functions can also be combined, and we will also show that here. And all the branches in Leap share the same set of functions, which means there are some that are slightly special, but in general, especially ones that we are showcasing here, can be used both in different demand sectors, transformation, resources, key assumptions, everywhere. It's more or less the method of using math in Leap in simple ways, but that is how we will do that. As stated in previous videos, the functions are done in the functions window, which is in the analysis part of Leap. These here are all different functions. Don't care about the color right now. We will get to that in scenarios. Depends on that. These are some of the scale and units that we specified for the functions. We will also get more into that. Up here, we can see what kind of different variables, meaning what kind of functions we could input for. So in this case, all the functions that we have given are all for the activity level of different places in our model. So we can see that all just by looking at this window. We also will specify functions for the final intensity, and in this case also cost, because we have cost on in this window. And of course, all variables is just a place of showing all the variables for this specific place. I usually don't use that because it gets a little heavy and confusing. Here we have changed to a different example where you can see that we have quite a lot of different variables we can change in this, and we have quite a lot of different functions. So here we're just going to see what happens if we actually change a function in Leap. So here we are in a household, and we are going to change the residential fuel oil function here, which is now an Interp function 24010, and year 240, and it's set to 10. Don't worry about that, we'll get into that in a second. That will look like this in a total window. Notice the relationships between the three different technologies: electricity, residual fuel oil, and natural gas. And we are going to change the residual fuel oil, and quite a lot. So now, just remember, it is starting in 40, and in 2040 it will be 10. We're going to change that into a new fuel. Same method, Interp, but we're going to change it in 2020 it's going to be 40. In 2025 it's going to be 5, and in 2040 it's going to be 10. So we're going to have the same endpoint, but we are changing wildly how it looks like. And as soon as we hit enter on that, we have some pretty major changes. And here we can also see what it does in the interpolation or interp function. So in this case, we have a starting point because that comes from a different scenario, the statistics scenario, current accounts. And then we specify in something that happens in 2020, specify what it should be in 2025, and also again what it should be in 2040, our last year. And it will then just linearly find out what's in between these. Here we also have a nice application of the remainder. So in the remainder 100, which is for the electricity, as we see up here, that means that you can see the electricity just shapes itself after we have given something for natural gas, we have given something for our residual fuel oil, and whatever is left to reach to 100% is taken by electricity, and that is what the remainder does. It just makes sure that everything is 100 in every single year, which is quite smart. We will get more into that in a second. So almost all functions are given as a multi-year function syntax. That's what I showed you just before. So in terms of the interpolation, you can see we have first a year, value, year, value, sorry, that's 102. Here we have a year, value, again, year, value, so on until we reach our 2050. For growth, that's slightly different, the same as growth as, if I'm not wrong. Growth cannot be used in the current account because current accounts only, it assumes that you have data because it should be statistics. So there we just say from what we have from the last statistics year, which is the year before first scenario year, if you remember that from our settings, then from then on it will grow by a certain starting percentage. So here it's growing at 1% per year, and then in 2020 the year we will change that to be forward 3% per year, and that will occur until 2035, where it will start at going 5% a year. So that is what we have here. In most functions we have a year, a value, year, a value, and so on until we get that. And Leap will not accept everything that's incorrect, so it will tell you if you have the, especially if you have the check as you type function on, which you can see in a second. So just to go through the most important projection functions. Some of these cannot be used for statistics, some of them can, but we will go through them nonetheless. So the one that we use absolutely the most is the interp function. So the interp function, as showcased in the example before, is just very simple. You give it a year and a value, and then you have another year and another value, and maybe a third, fourth, whatever, values and year pairings. And then it will have straight lines between it. Smooth will do more or less the same thing, but it will try to smoothen it out. Step, it will do in incremental steps. So that's very practical if you have a plant of some sort coming online. For instance, we know we are going to have a new nuclear plant or new coal plant coming online in 2025. then that will be turned on, and suddenly you have new coal capacity of 1 gigawatts, for instance, or a new offshore wind park, or something else that's not quite fluent. Growth, that's just a growth function, percentage growth function. And growth as, that means it will grow the same as another place, as somewhere we have a link. We'll get to that. And then you can implement elasticity. And the remainder, of course, it fills a sector to achieve a specific number every single year. Usually that number is 100 when we have to do with shares, but it can actually also be anything you want. You can specify that. So, just to iterate, here we have, you can see I put up a fake example with a projection test. And here we have a function that's interp. And here we have a function that's in smooth. And here we have a function that's step. It's important to note, if you notice, that all the year value pairs are exactly the same. So the years that it occurs at is 2020, start year, then 2020, which is probably around here. It's difficult to see because I didn't put it on. 2030, 2035, this must be 2035, and then at the end 2040, something like that. So this is how the interp function looks. Whatever we do, it just puts a straight line between them. When we then have this, you can see we actually get a little bit of a different result here, because most of the way, because we make very little changes, it's more or less the same. But actually, if you look up here, you can see it actually increases over what we had before. So we have a larger maximum. And that means you actually have to watch out for smooth a little bit. It looks nicer. It might give a more natural data prediction. But especially if you have a sector that goes both up and down, then you can have a risk of an overfitting. So it will actually go down to minus. If you have a sector that decreases and then increases, it might actually go down to a minus area and you will get an error. Again, completely flat until it changes from one year to another. Something came online. Very good for big transformation projects, a new refinery, a new power plant in demand. It could be a new cement plant, for instance. It could be a new sector that's starting up, a new method that is a high capacity method. So something came online, that's where it's really useful. They can of course both be, now I only increased it in step, but of course they can be both step. We have to have it here a little bit, we have to have a step down here as well. So that is a retirement of a big capacity plant, for instance. In terms of growth functions, I will come to that next. The important part is they cannot be used in current accounts, only in predictions, because current accounts should be shown as statistics. The current account scenario is only for statistics. So we do not define that in growth rates. We can define that in absolute numbers. That's why. So that growth is only for what in predictions. In all scenarios, the first growth that I shown before, that applies to the last current account state number. So that's the year before first scenario year. Usually that means the current year you are actually in when you're making the model. So in this case, it would be 2020 because we might have the data for that, or 2019 because that's our latest data year. And it cannot be applied where the unit is percent. You cannot have a growth on a percent unit. It will not let you do that. I think that can be changed in settings, but it is actually for good reason, because it gets murky very quickly in terms of when you put that into the percentage. So there you would more likely say if you want a specific number of percent, it will grow to a different percent. So you will apply that as an absolute percentage range. So here I made a small example as well. So you can see here we have a, here is more about the actual formula. So here we have a growth. We start with a certain number. Here it is the growth here. We have 100 in this case. And then it steadily grows with 1% until we reach 2020 this year. And you can see then the growth increases because now it's 3% until we hit 2035. And then you can see it goes even higher because now we're at 5% growth. Now, with the growth as, I put in a reference. We'll get to that in this video in 2 minutes. So now we have the same growth rate as our income, in this case, our gross national income. And I put an elasticity of 57% on. And that means I know that our gross national income is input to be something higher, but it will have the elasticity under to be 57%. And that is really good for industrial sectors you project will grow with the income, or where there is an elasticity. It's also something you have to be very careful with. I have seen a special transport number that was supposed to grow with income, but actually in reality that means that in the end you will have more cars than people, because the purchases of cars does not follow gross national income with an elasticity. There is a maximum number of cars you would want, a person would want. So this is the two main growth functions. Now, most functions can be mixed. So here in this case, I set up a function. So this is a function in Solari that I call growth func test. And here you can see I have an Interp function in one end. And then I I add on a growth function on the other end. And that just means I start from somewhere, and then I increase both the number and the growth. And you have to mess with that a little bit, because otherwise it will be very rapidly increasing. As you can see, this is a small sector that becomes very fast, very big, despite me having starting in 2010 with 103 and in 2030 being 2. So that's a rapid decrease. But because I also have a growth rate on, it also implies a great increase. It's not, this particular function pairing is not particularly useful in real life and real model making, but you can do this with almost any different manner of functions. So to help you make functions quite nicely in Leap, there is this builder button you can push. So if you click on a function, so here I have marked just by clicking on the urban function, and then I can open the builder, and then I have two very interesting functions here. So I have the branch variable function, and then I have the functions windows as well, which we will now talk about. These are two different things, but they're very practical if you need help building a function. So first, here we have a little video showing the functions video. So if I go in, click a certain function. So here I'm going to be working with the efficient industry, and I can see that comes from another scenario called the baseline scenario. And I want to change that to be based on my baseline scenario. So I'll go into my functions window. And in this case, I can choose a lot of different things, but I'm choosing modeling. And then I will find a function called parent scenario, I think it's called, parent scenario value. And that's what I did there. And I can say, so now it will follow the exact value from my parent scenario. So that's basically being the same, but then I can work with that. So in this case, I want it to be whatever the value was in my parent scenario. I want it to be that, but multiplied by 2. So you can see that now suddenly, compared to my former scenario, which was around here, now it's just a double of that, which is quite smart if you want something that's in relation to. Let's say you have a bit of a scenario where you have a policy that the uptake in BEV vehicles has to be twice as what's expected today, because you're putting in a policy that would support that. That is a way you can actually just put that in. And of course, you can mix that with an Interp. So you can have the twice in 2 years and 4 times in 3 years, and then interpolation between those. You can do a lot with these things. That's very, very smart. Here in the branch variable window, we are looking at linking. So here in the natural gas, I want that to be hinging on something else. I had to come up with a fictive example here. So here I can see where I am in the function. So I can see, hey, I want that to be dependent on population growth rate, maybe, or in this case, I think I'm choosing urban total activity. So I can choose that. Depending on what I can choose both from result variable, so that would be results from last year when it calculates, or other data from otherwhere in my model. And I can apply that. In this case, it's going to fail because it doesn't fit together, because one is percent and one is which is maximum 100. And you can see Leap actually warns me of that, which is quite smart. But you can use that in different ways. In real models, this is very, very applicable, but I haven't been able to use it well here in the Freedonia training model. So to more of a real scenarios, here I have real examples of where I use both different functions and linking examples. So here I have a base year multiplied by an Interp function. And that just means this is my first base year value. So whatever it is in my base year, I can then multiply that by a different factor on every given year. So I know in 2030 for this particular thing, I want my value to be 1.27 times what it was in my base year. So that's what this function means, and that's just by linking two functions together, which is quite nice. Also, in this case, in the middle, right here, I actually have this is a link. So this is in my key assumptions, and I have a folder under that called transportation, folder under that called passenger text share, under that EV. I take that, divide that by 100, and then I multiply that by a very large number. This is the base sales of my first year, so that could also be a base year value, but in this case I just put it in as a fixed value. This will actually make updating more difficult because I have to change it more places probably, and that's but that was what we did in this model. And then I multiply that with here I have a similar key assumptions, and I have a vehicle sales development, which is a factor, and this is a absolute number upstairs on top of what my sales was, or what my number of vehicles was from a specific technology. So that's an absolute number. This is a factor, and this here again, this is my province area factor, because this is a model where we have multiple regions. So this is also a factor. So here I successfully multiplied a large absolute number with a factor which is less than 1, and another factor which is less than 1. And that means I, in the end, have my sales development going forward for a particular technology based on the base year, the technology share that is in the future, and the base and the general vehicle sales development factor. That's which can be more or less than 1, and also divided that into different provinces, so I can put it into a provincial level quite easily. So that's what I did here with just 3 different linking places, and I can spread this to multiple places in my model. In this case, it could be multiple vehicle types, so that could be both cars and trucks and MPVs and pickup trucks and so on. So I can share most of this. Most of this can be shared, which is a very good thing to have. Here I did the same. This is with fuel efficiency. So I put in a standard. So that is a fixed for the standard for the current year we are in, so the first scenario year. Then I put in a factor larger than 1 or 1 on an index on the size. So here I put it as a car. So that means I can also have this for MPVs, which is a larger vehicle. So it can be factor 1.1, for instance. Here I have it for a motor factor. So here you can say the standard is ICE petrol, but I can also have that as something else. And these are different factors that I have which improves the fuel efficiency of a specific motor type. And these are shared between a lot of different motors and vehicle sizes. And I can just print these in. And this is a yearly factor. And then in this, all of this can tell me what the fuel efficiency will be for a given vehicle in a given year going forward, just by linking things together, by multiplying them together. So this is a real life scenario, which is quite practical. Might be slightly hard to read if you're not familiar with it already. So to make it easier for you to actually work with, this is from a similar model where I use this functionality, and we can show how you can actually look at some of these like larger functions and combined functions and get an overview of them. So here we have a large function which is in our car 4x4 example here. You can see the function works. We have charge, we have valid tables for it. If you go into the builder, you can now see we have actually an overview of the full function, and we can divide it by putting extra spaces or divide it into lines, and we can have a better overview of that. If you have a very long formula that doesn't really fit, you can now see the whole of it. And it will also ask you to make sure that it's okay before you go on. Here in Elaboration, we have we can see all the things we're referencing. What value are those and where does that come from? If you go up here into car 4x2 in benzene, which is gasoline, which is one of the standard example, we have the opposite side, and this is all the places that references where we are actually now. So you can see that the car 4x2 benzene actually feeds information to all these other places in our model. In this case, it's all the different vehicle types. So we have 4x2, affordable energy efficient vehicle, which is an Indonesian specification, double cabin large pickup trucks, pickups, sedans, and buses. So that's something to do with the fuel economy. And you can see we do that in different scenarios, and we do that for different fuels because we also have them for bio-premium, which is a biofuel, for plug-in hybrids, and for diesel, which is miniac solar. So we can both see where things come from, and if we are in another place where things go to, which is a good way of having an overview. So that means in this particular case, if we change the value that we have in this function up here, we know it will affect all of these places here, which is in this case only fuel economy, but in a lot of different vehicles. So this is a way that we can very rapidly correct things in our model. That means that we fit together. So if you think that the general engine technology for gasoline car, for gasoline vehicle improves differently because something new has come to light, well, we can just change it one place, and everywhere else in the model where it's applicable, because we put the right linking in, as we can see here in the elaboration, we can then they all will change too, and that will have a larger effect on our transport model on purpose, which is a good thing.